As we saw in the last lecture, one way to turn a predicate into a statement is to replace the variables with numbers. And another way is to add quantifiers. There's words that refer to quantities like some or all. They're going to define a specific set of objects or elements for which the predicate part is true. So the new symbol at the beginning of the sentence here is the universal quantifier, and it's read for all or for every or sometimes for each, right? And it's used to describe a property that is shared by every object in a domain. So in this case, the domain is the set of even numbers, right? And the second part here defines a property that every element in that set has to have. Okay, so here we have a formal definition of a universal statement. There's a lot going on here, right? So let's parse it out one piece at a time, right? So first, a universal statement has two parts. It has a predicate and a domain. Right, now, referring back to our previous example, right, even numbers is the domain, and x is divisible by 2 is the predicate. Right, so the next part of the definition just sets up the notation, right, which we've seen already. So I would read this, for every x in D, we have Q of x. And the last part here tells us how to determine whether or not the universal statement is true. Right? And being able to do this is the key thing that makes this a statement rather than just a sentence. Right? And our rule is that Q of x is true, if Q of x is true for every value in the domain, then we would say that the statement is true. And on the other hand, if there's so much as one value, right, a value of x for which Q is false, then the whole statement is false. Right, now notice that we aren't requiring the statement to be false for every value in the domain. All it takes is one bad apple, right, called a counterexample, to falsify the entire statement. Right, so for this specific statement here, since every number is in fact divisible by 2, our conclusion would be that this is a true statement. Right, so notice what I did here. Right, all I did was replace even number with real number. In other words, I made a change to the domain but kept the predicate the same, right? So now think about what that did to the truth value of the statement. 3 is a real number, that is, it's in the domain. However, 3 is not divisible by 2. So because there exists a number in the domain for which the predicate Q is false, the entire statement is false. Now, it's true that there are other values in the domain for which Q is false, as well as some for which Q is true. But when we're talking about universal statements, one false example was all you needed to determine that the statement was false. And this one false value here is what we refer to as a counterexample. Right, so universal statements are a good first step toward the kind of language that mathematicians need to talk about groups of objects. In the next lecture, we're going to add to our toolbox with a second kind of quantified statement called an existential statement.